So to understand a little more what makes water unique, you need to understand the water molecule. So here we have a bunch of O's. Now what we're going to do is add some hydrogens, because remember, it's H2O! Yes, I watched too many commercials when I was growing up. So, yes, these do look like little mouses or little chipmunks, or whatever the heck you want to call them. I like having a mutant zoo of molecules. That's kind of my style. I also love writing upside down with no training on how to write upside down. That is also my style. You know, this is a chance to have, like, a style makeover. All right, so the thing is that the electrons that are in orbit around the hydrogen nucleus are tied up, bonding to the oxygen. Thus, you have this positively charged proton inside the hydrogens, giving your hydrogen atom a positive charge along here. And meanwhile, because you have these hydrogen atoms tied up with the tying up some electrons, the remaining electrons are all sort of like gathered down around the far end of the oxygen. And so you get a negative charge on the oxygen atom. And so because of this, these atoms, these molecules of water, can kind of pull on each other and exert a little bit of a force that kind of holds them a little bit together. It's going to take a little more heat and kinetic energy to sort of break them apart and make them fly off different directions. So the hydrogen bonding changes how the water behaves in an energetic fashion, especially as water relates to heat. So the first term we're going to introduce to you here is heat. This is thought of as the total kinetic energy of molecules in motion in a substance. If you are a solid, you kind of dance around. If you're a liquid, you're kind of rolling. And if you're a gas, you're flying all the room. I've got some Avogadro's number of molecules flying around me, bouncing off my face as we speak. It feels wonderful. In fact, if I did not have those bouncing off my face, I'd probably explode like the bad guy in Total Recall. And I'm sorry. I have a class to teach, so I'm not going to do that for this video. So to understand heat a little better, we're going to break it down into two terms. We're going to start with sensible heat. This is energy received or lost from a substance that results in a change in the average speed of molecular motion, but not the nature of molecular motion. So it's kind of like if you see a bunch of kindergartners sitting on the carpet, maybe not kindergartners, but it's like, here I am, kind of grooving, and I suddenly get really more excited. That's kind of sensible heat there kind of happening. It's like you turn the burner on, the pan gets hot, but the pan does not melt. If the pan does not melt, if the pan melts, I'm going to be worried about your cooking and probably not take food that you offer me. Let's hope that doesn't, but point being, the substance stays fundamentally the same, it just gets hotter. So another way to think of this is heat capacity and or specific heat. This is the energy required to raise a given mass of a substance a given amount. Turns out, by the way, one of the unique qualities of water is that it has an extremely high heat capacity / specific heat. This is one reason you might want to use oil in your cooking, because oil will require a lot less energy to get up to a certain temperature. This is also compared to water. This is also why it's a lot easier to get your frying pan hot than it is to get a cup of water hot, as it takes a lot more energy to raise the temperature of a small amount of water than it takes to raise the temperature of a cup here. So let's start listing these properties of water that make it unique. So there we go. So the first property of water is going to be high heat capacity. This little chart will help you start to appreciate just how high the heat capacity of water is compared to other substances. Water's about takes twice as much energy as oil to heat up. Air has about a quarter the heat capacity of air. Remember that air is also quite a bit less dense, at least around here. Copper, by the way, has a very low heat capacity. Iron, a little bit higher. Granite, which is what makes up most rocks, also has a fairly low heat capacity. This is why a rock in the sun on a sunny day often feels so nice. But if you've been someplace that actually gets cold in the winter, you know that sitting on a rock is about the worst thing to do because you will freeze very quickly. Rocks lose heat quickly and gain heat quickly. Water is takes a lot more energy to get hot or get cold. So the second term we want to introduce here is one called latent heat. Latent heat is energy gained or lost with a phase change. What do we mean by phase changes? All right, let's take a look here back at our little PowerPoint land. So water goes from ice to liquid. That is a phase change. Water goes from liquid to vapor. That is a phase change. Sometimes in very high altitudes, or if you've ever seen frost on your windshield, which if you live in San Diego, you might have never seen frost. Where I grew up, we had quite a bit of it during the winter. That is also an example of phase change. And the one thing you notice, like if you've ever been burned by steam or something else, is that, yeah, it really hurts because there's a lot of heat in that water. Or perhaps my favorite metaphor is if you have a glass of lemonade on a nice sunny day, as the dew condenses on the glass, the lemonade ceases to be cold. At first you think, oh, that nice dewy glass of lemonade, but no. There is actually research underway right now in somewhere in Seattle to design a lemonade glass that does not allow dew to condense on it. The idea being that if you can inhibit the condensation of dew on lemonade glass, the lemonade in the lemonade glass will stay a lot cooler during the summer. Because what's happening is your water vapor is turning back into liquid when it condenses, and that transition is releasing a lot of latent heat. Because water, not only does water have a high heat capacity, it also has high latent heat. So make sure to write that down on the unique properties of water. High latent heat. Yeah, alcohol or even oil, all these other things do not quite have that same property. The other reason are even chocolate. You've all seen chocolate melt. When chocolate recrystallizes, it does not seem to, you don't see as much a gain and loss in heat. And again, it's sort of puzzling because, like, water's the substance most people see melt and refreeze most of the time, and they see most phases of it. Most of the substances, we don't see them freeze and or vaporize the way water does. So we think water's kind of normal. No, water's unusual. And again, this is a consequence of its hydrogen bonding. This goes with both going from ice to water, or water to ice, solid to liquid, liquid to solid, and from vapor to water. Because what's happening is not only kind of getting those molecules to move differently, but a way to think about like latent heat is sort of like kindergartners on the floor. If they're sitting all in a row, they're pretty low energy, but then they start to wiggle because that's what kindergartners do. Then they start to kind of roll, and they get out of their seats. And then finally, because I know this because I'm a really bad substitute teacher, is that they start running all over the room. Seriously, I was subbing for kindergarten in a city that shall be unnamed, and after lunch they came in. They're great at moving the furniture. We had to move the furniture because there was going to be 3 kindergarten classes all in the same room, and we had to make room for them. Oh, they were great. They were better at moving the furniture than I was. However, upon moving the furniture, they then thought it'd be cool to climb all the furniture that was stacked alongside the room and start dive bombing off this. At one point, I asked one of these sweet little kindergartners, please stop dive bombing off the furniture and take a seat so we can get ready for the assembly. This sweet little kindergartner, being very high energy, moves to this transition of dive bombing off the furniture like a molecule of gas to sitting still like a molecule of science. But in the process of doing so, the little jerk hit my foot with his hand, and it really hurt. These guys got a lot of energy when they're flying around. They may be like wee little people, but man, And the best part was, just 10 minutes later, seeing him in the assembly, singing songs about peace, love, and cooperation after this guy's like, what, seriously? Dude. Yeah. So again, with water, you're breaking the hydrogen bonds to evaporate it and melt it, and then you're reforming those bonds. When those bonds reform, you're releasing energy, much the way that little jerk in kindergartner was releasing energy when I finally got him to sit down. And so what this means globally is that when you're near body water, we know this in San Diego. This is why everybody wants to live here. We're next to a big body of water that generally stays about the same temperature between winter and summer. In fact, it's often joked we don't have seasons here in San Diego because we do. I'll explain that after spring break. But yeah. But this is why we don't have our equatorial oceans boiling. This is why our polar oceans do not freeze solid. We do get sea ice, though we're getting less of it generally each year. And because of this, because of these properties, life on Earth is possible. If we had boiling oceans at the equator and frozen down to the bottom oceans at the surface, so high latent heat is an important property. Now the final one is this one, density. Because of these hydrogen bonds, water is one of the few substances on the planet that is less dense in solid form than it is in liquid form, because as these hydrogen bonds start to form crystals, they form a fairly open structure that makes has a lot of empty space. When you have a lot of empty space, your density decreases. So, final property of water is that lower density as a solid. That is your third property of water. Lower density as a solid. There's a fourth property I want to talk about. You kind of see it in the slides that I was skipping over. Let's go back to some of those. So when you have water, water at in a vessel. Let's do a little drawing here. So if you're looking at a glass of water, you got all these molecules in here, and you're the ones in here are being pulled on all sides. The ones at the surface are only being pulled on from below and their sides. Meaning, if there's a little less force flowing into the glass, it's a little easier for one of these to fly off like molecule of gas. As a consequence, water has a very high vapor pressure for the temperature given to its melting point. High vapor pressure. You also see up here a very high surface tension. This is why bugs can skitter along the surface of the water. Same phenomenon. Hydrogen bondings. Hydrogen bonding will hold that water together, and that's what allows things to skitter along the surface. And of course, the other one, which we explored earlier in our And the Crazy Cat Lady lecture, is that because of all those hydrogen bonds, water is very effective at breaking down ionic bonds. As we saw when And the Crazy Cat Lady visited Disneyland, and water, symbolic of Mickey Mouse, caused Anne and her cat to have a breakdown. All right. That's all, folks, for this portion of the lecture.